Yes. So after our discussion on the basics of phase diagrams, let us come to the very important phase diagram, which is the iron carbon system here. So when I start talking about the iron carbon diagram here, which we say is called as FEC diagram, or sometimes more specifically, this one is called the FE3C diagram, because if you look at the extreme right hand of this phase diagram, we find that you are ending at not going to carbon percentage of more than 6.7%. And a compound which is formed at 6.7% of carbon is called as iron carbide, or also referred to as cementite in our discussions later. So, so when I look at this phase diagram here, and let's start looking at it from the basics of our earlier discussions on the phase diagrams, and we will start building upon this diagram slowly. Okay, so you have the temperature scale given to you here, and here is the composition scale. So before starting discussion about the FEC FE3C system here, iron carbon system as such, we understand that pure iron, when you call about pure iron here, it undergoes phase transformations, where we have already said that with change in temperature, the crystal structure of pure iron keeps on changing. So when I talk about pure iron here, means actually we are here when you have 0% carbon in it. So the phase diagram itself shows you some of these, or all the changes which are happening here. So at room temperature, your pure iron Fe happens to be in a BCC structure, which is also referred to as the alpha iron. It's called the alpha iron. So we find here that at room temperature it is in BCC structure, and we say it is called alpha iron. So if you read on this scale, you find that here I have alpha iron going on, and at nearly around 912 degrees centigrade. So after 912 degrees centigrade, we find that you go into the second the iron undergoes the first phase transformation, where from this goes from BCC to FCC, and we call it as gamma iron. So we find this first transformation happening here at this point for pure iron. Keep it in mind. So we are talking about only the extreme left hand side of this phase diagram only. So from alpha at 912 you go into gamma, and that at around 1394, pure iron at 1394 goes into again into BCC crystal structure, which is shown here as delta, or it is also called as delta ferrite. So you had alpha ferrite at room temperature. Alpha ferrite at temperatures greater than 912 goes into gamma austenite, gamma which is called austenite, and austenite, which you keep on further heating it, further goes into the BCC crystal structure again, which we say is known as delta iron, or also called as delta ferrite. Now we have, so at 1394, we say it again goes to BCC, which is called as delta ferrite. So this happens at high temperatures, and we may not be interested about this particular phase of iron that much. You may have noticed here that you're talking about alpha, gamma, delta. There is nothing called as beta iron here. So why doesn't we talk about the beta phase also? So I'll explain it in a moment here, that why doesn't that happen. Okay. So with respect to this alpha iron and gamma iron and delta iron, we find further that the solubility limit of carbon in iron is varying. So we have seen already in our previous discussions that carbon forms an interstitial solid solution. It forms an interstitial solid solution with iron. So when I say interstitial solid solution, means now you can have the iron located here in any of the interstitials, which may be tetrahedral or octahedral. We have already seen the size of the octahedral voids and the size of the tetrahedral voids in the case of your BCC as well as FCC structure. So we already know that. And we have explained it already that what is controlling the maximum solubility of iron in maximum solubility of carbon in pure iron happens to be the interstitial types and the size of the interstitial spaces. So in your FCC iron, the octahedral sites are larger, and that is why the solubility limit of iron, of carbon in the gamma iron happens to be very large. So let's look at this statement with the help of the phase diagram. So when you talk about this phase diagram now, let's slowly start reading it. Okay, so you have pure iron here at 0% carbon addition. We now start, let us say, looking at let's first look at the lines which are there in this phase diagram, and then we talk about some of the reactions that you had already seen about the eutectic reaction as well as about the eutectoid reaction. So let's start reading it from the top. So I have liquid region here. So I have liquid phase, which we say is L. Means now I have this line, which is called as the liquidus line, which simply says that above the liquidus line, only the liquid phase is existing. Okay, is it right? Okay. Then after that, you have now if you apply, I talked about one rule yesterday when we talk about is the 1-to-1 rule. Means if you draw a horizontal tie line or a horizontal isotherm line, which is on the left hand side, there is only one phase. On the right hand side of it, there is the another one phase, not the same type, but a different one, single phase. Then in between those two, there will be a two phase region. So if you start applying that here, we will see that in this region that you see here, you have delta ferrite. So there is a single phase region. So I draw a line here. Let us say I draw a line here. So it has a liquid region here. It has a delta region here, which means the in-between region must be having delta plus L. It must be delta plus L. Okay, let us see. Similarly, if I draw a line here now, it says it has L region here and it has the gamma region here. Between means on the one side you have one single phase region, on the second side you have the second single phase region. 1-to-1 rule tells me that in between you must have delta plus L. That is, this both of them shall coexist. Delta plus L shall coexist. So that is how you keep on populating this diagram here. So you have the liquidus line that you have now. You have delta plus L line, means delta iron plus liquid, both are coexisting. Now in this diagram, try to locate the first reaction that we referred yesterday, eutectic reaction. Eutectic reaction. So keep it in mind, what was a eutectic reaction? We said a eutectic reaction is an invariant reaction at which the three phases are coexisting. That is, or another way to say that is, a liquid phase on cooling or heating also gives rise to two solid phases. So a liquid phase on cooling or heating gives rise to two solid phases, means S1 plus S2. So can you find any such reaction here where a liquid phase is directly converting into two solid phases? We find that is happening here at this point. Just remember the another definition of eutectic was a low melting point, and this happens to be the lowest melting point here that exists here. That means that 4.3% of carbon and at 1147 degrees centigrade, what is happening? There is a eutectic reaction happening here. There is a eutectic reaction happening here. Invariant reaction means it will happen only at a carbon percentage of 4.3% and a temperature of 1147 degrees only, nowhere else. So it is an eutectic reaction, and what is happening during this? The single liquid phase is transforming into two solid phases. The two solid phases are gamma, which we say is austenite, plus the second phase which is happening is Fe3C, that is cementite. So at the eutectic reaction of 4.3% carbon, which is the having, again incidentally, if you see, this is having the lowest melting point anywhere in the diagram. Anywhere else, if you want to have any other composition of iron plus carbon, the melting temperature will be higher. You can see that it will be following the liquidus line. But the liquidus line is the lowest here. And that is why we find that this is the lowest melting point available to us, and this is the eutectic point. And this composition is called as the eutectic composition. This is called as the eutectic composition, at which when we say that single liquid will transform into two solids. The two solids here are austenite plus cementite. Okay, so this is the first reaction that is visible to us. The second one, which I referred to in my last class, was a eutectoid reaction. A eutectoid reaction. So a eutectoid reaction, we said, is that reaction in which a single solid phase, S1, on heating or on cooling, it transforms into two solid phases. A single solid phase transforms into two solid phases, or vice versa. And here is where we see that is happening at this 0.76% carbon. At 0.76% of the carbon here, we find that is happening. What is happening here? The single phase, what is this phase? Above 0.76% carbon and at a temperature. Now the temperature happens to be 727 degrees centigrade. Again, an invariant reaction which happens at a carbon percentage of 0.76% and only at a temperature of 727 degrees centigrade. What happens is a single solid phase, in this case austenite or gamma iron, when it is cooled, when the carbon percentage is 0.76%, when it is cooled, it transforms into two phases, into two solid phases. The two solid phases are alpha plus Fe3C, that is ferrite plus cementite. So it undergoes into ferrite plus cementite. So single solid phase gamma goes into alpha plus Fe3C, and that is what is happening here, and we call it as a eutectoid reaction. Anywhere else that you find that not at 0.76% carbon, this is not happening. So if this is the eutectoid reaction, this is the very important reaction as far as the heat treatment of steels is concerned, and we will come back to it in details. But before going to that discussion, let us look at this diagram further. So we have seen that this happens to be the eutectic point at 4.3, a eutectoid point at 0.76, and I find that there is an isotherm. So this is the 727 degree isotherm is called as the eutectic isotherm. Sorry, eutectoid isotherm. Eutectoid isotherm. And the isotherm that is available to us at 1147 is then called the eutectic isotherm. So you have the eutectic isotherm as 1147 and eutectoid isotherm at what we refer to as 727 degrees. There is one more important reaction happening here, which I'll explain just now, which is called as the peritectic reaction. A peritectic reaction happens once let me just take it away and so that there is more space. So we have one more reaction which is called the the peritactic reaction. What happens in a peritactic reaction? That one liquid plus one solid phase on heating and cooling will give rise to another solid phase. One liquid plus solid phase on cooling gives rise to a single solid phase, or vice versa. And this peritactic reaction is visible here. It happens at 1493. This peritactic reaction here happens at 1493. And that is why I find an isotherm available here. I find an isotherm here. What is happening at this point? We already said that this point, this region here was delta plus L. So I have liquid plus S1, liquid plus delta solid phase. On cooling, this is the point at which the peritactic reaction takes place. On cooling here, it transforms into the second solid phase, which we say is the gamma phase. So below this is gamma. We already seen that. So below this is all gamma here. So delta ferrite plus liquid transforms into gamma austenite, and this is the third reaction, which we say is the peritactic reaction, which happens at 1493. So just to remind you the important reactions in an iron carbon diagram, looking from the, let us say, the lowest temperatures. The first one happens at 727, called as the eutectoid reaction. Second, called the eutectic reaction, happens at 1147. And third, the peritactic reaction happens at 1493. Out of these two, eutectoid reactions and eutectic reactions are more important to us. Peritactic reactions are not that important, and we will not talk about details about this reaction. So, with this background, so let me take away some of the notations from here so that it becomes more clear, and then we can proceed further. So we had the liquid. So you had the liquidus line. This is also the liquidus line here. So you have the liquidus line. Above that is only liquid. So you have the austenite region, again the solid region. The maximum solubility of carbon in austenite happens to be here at 2.14%. Because after that, if you keep on adding more, and it happens at a temperature of 1147, below that, this is the solubility line. For alpha ferrite, this happens to be the solvus line. So the maximum solubility of carbon in alpha ferrite is just 0.022%, and the maximum solubility of carbon in austenite is 2.14%. And we find that it is around 100 times more. So in this region, so this is the region. When I talk about this region only, this is the single phase region alpha. After that, you find the two phases are coexisting. Here I have the single phase region gamma. Here I have in between these two, so you have the 1-to-1 rule. So if I draw a line here, it tells me that if this is alpha and this side is gamma, in between this must be alpha plus gamma. Very clear? Alpha plus gamma. Similarly, we have seen this is alpha plus liquid. And after the maximum solubility line is this one. So when you keep on adding more carbon into it, Fe3 phase precipitates. That is, now it will be gamma plus Fe3C in this region. So I have a particular composition which is happening at this 0.76%, which is called the eutectoid composition, and I have another composition at 4.3%, which we say is called the eutectic composition. And I have the third reaction, which we say is called the peritactic reaction. So we have the peritactic reaction here, you have the eutectic reaction here, and you have the eutectoid reaction here. Okay, so That's all in the first part of the lecture that we are required to understand, and we will continue this in our next lecture.